Good evening, everyone. My name is Sylvain. I'll be your host for tonight. So along with the team, we have Douglas here. We have Truni, Sasha, Jan, and a ton of TAs as well. We are super excited to welcome you for this fifth demo day combo tonight. So tonight we'll have data science as well as web development students pitching. That's 28 students split in 6 and 2, 6 for data science and 22 for web development. I'd like to introduce a little bit Le Wagon before we get started. So as maybe most of you know, Le Wagon is a worldwide coding bootcamp. We are in 20 countries, 20 plus countries, 44 cities, and just a little number today. I think we counted just before demo day. We actually have 20 batches graduating all over the world. So that's roughly maybe 300 to 500 students. People are graduating in Berlin, in South America. People are graduating in Paris, London, pretty much everywhere around the world. As well as in Tokyo. That's it. So let's talk about Tokyo a little bit. Tokyo, we have a big milestone tonight. We've been around since 2016, so it's been 5 years we've been running this. It's been an exciting journey. I don't know if exciting really describes that journey properly. And tonight we have a big milestone with everyone graduating tonight. We're going to pass the 400 students mark in Tokyo. So again, I think we deserve this time a big round of applause. Cool. What is Le Wagon? So as I said, Le Wagon is a coding bootcamp. And what do? We help people change their life. We help people transform their career through code. And we do that with 2 different programs. One is a data science program. The other one is a web development program. And both of these programs, we offer them in 2 formats: part-time, 24 weeks, for people who maybe have a full-time job on the side who cannot afford to take 9 weeks off, and a full-time format, 9 weeks intensive. And actually, everyone tonight went through our intensive 9 weeks program. So we're going to kick things off with our data science batch, with our data science students. So I'd like to give you a little bit of facts about them. They started studying with us 9 weeks ago. They started with Python. They went through data analytics, machine learning, deep learning. We're going to talk a lot about deep learning tonight, so I hope you're ready. I hope you have Google open to Google all those technical terms. And they went through data engineering to get to the final stage of the bootcamp, which is the final 2 weeks. And that's what they're going to present tonight. Those are the 2 projects that they built during the final 2 weeks. This batch was very special. We had 6 students, and it was a full hybrid batch, which means we had students joining us on campus every single day, as well, wait for it, as well as 2 people, one joining us from, I think you won't guess it. We had someone joining us from Alaska, so I'd like everyone to say hi to Larry, who is in Alaska right now. Hey, Larry. And the second person joining us from Melbourne, Nadia. Nadia, we're looking at you right now. Nadia, super happy to have you. We also had teachers remote. Alec is with us. He's in Melbourne as well. Maybe he's actually sitting next to Nadia. Thanks a lot for all the hard work, Alec. It was amazing. And I think that's pretty much it for the data science intro. I think we're pretty much ready to get started. So without further ado, I'd like to welcome Lorcan on stage for ExoHunter.
Good evening. Welcome to Demo Day, batch 728, I think, for us, and 727 for all the web dev guys. It's pretty exciting. It's been a weirdly short 9 weeks, but when we realized we were starting, we decided to do a pretty light-hearted, easily digestible topic. It's all about humanity's insatiable desire to know more about meaning and existence, and our unquenchable thirst to learn more about the universe. We're hunting exoplanets. So for anyone who doesn't know what an exoplanet is, it is any planet that orbits a star that isn't our sun. Okay? But why do we even care about exoplanets? What's so important about them? Many of you have probably seen this equation. Some of you might not have. It's called the Drake equation. That number n on the far left represents the number of alien civilizations we should be able to talk to. Okay? And number r represents the number of stars that there are out there. Now that's billions and billions. But F, that's the fraction of those stars that have any planets. And up until quite recently, we thought F was basically 0. Okay, but recently, actually, through new methods, we've discovered F might be pretty close to 1. Now, the implications are that there are probably billions of planets just in the Milky Way alone, orbiting stars. And how do we find that? So something called the transit method. Now, if we're lucky enough that a star does have planets, and the orbit of those planets is oriented such that every now and then those planets eclipse the star from our point of view, then the brightness coming from that star to us sort of fluctuates. So that little curve on the left called the light flux curve, there'll be a dip every time the planet passes in front of the star. Now, it's not the only way to find planets, but it is definitely the most powerful, and it's what we've based our model on. So at the moment, I said there are billions of planets, and basically the way we try and find them on different stars is that we just go through one by one, pass it essentially by hand. Okay? Now, if we took everyone and said, stop what you're doing, all your time is now devoted to looking for planets around stars. Everyone, that's surgeons, farmers, babies, everyone on Earth. If they stopped and just devoted all their time to this, we'd be here for centuries, almost a millennia, just to find all the planets in our Milky Way alone. So our goal was to develop an analysis tool, a research aid, that would help to cull as many sort of duds, planets, stars with no planets as possible, but without accidentally also culling off stars that do have planets. So this is our platform, the Exoplanet Hunter. You can input a light curve by dragging and dropping a CSV file, or you can search using a Kepler ID, which is a unique identifier for celestial objects that have already been measured and have their light curves available online through an interface called Light Curve. And it will download those light curves and analyze them using our deep learning model. And if we think that a star does have planets, we'll give you a likelihood, yes, we think it does. And if we think it doesn't, then unfortunately, that's a big no. But if it does have planets, and if that star is already in the catalog as having a deeper research done with confirmed planets, we also give you information about those planets here. So this star, around the size of our sun, does have 2 known planets already. And as this is a research aid, we've also given it the functionality that if an analyst or a researcher would like to display this information in a more visually appealing way, we also have a little animation that can be downloaded that displays the same information in a sort of easy-to-digest illustrative aid with the orbital radius, the planet-to-sun distance, and the radius of the star and the planets as well. But how does this work under the hood? The curves I showed you earlier on that demonstration slide was pretty ideal, very smooth, with obvious dips. This is what it looks like in real life. It's pretty messy, so the first thing we have to do is clean it up with a low-pass filter. A bit more usable, but we're looking for planets that orbit their stars. And they have very regular orbits usually, so instead of looking in this sort of time domain, we do what's called a Fourier transform, and we look in the frequency domain. So it looks a bit like a stereo equalizer. On the left, you've got low frequencies, and on the right, you have high frequencies. And that big peak, for example, represents a very high amplitude event with relatively low frequency. That could maybe be a planet. But we don't look at this by eye. We pass it through to our model, and that gives us back a probability, which we then pass using a threshold, exoplanet or no. So the model is a convolutional neural network for feature extraction, which is then passed to a series of fully connected dense layers. If you know, you know. If you don't waste time Googling it. But the important thing is, I mentioned transit method earlier, the dips, and I want everyone to look at these 2 curves. These are 2 stars, one of which does have planets and one of which doesn't. And I want everyone who thinks the star that does have planets is this top one to raise their hands. Okay, what about this one? Okay, well, yeah, it's pretty obvious. Look at the periodicity on this star, okay? Really obviously dips and peaks. This is just noise, okay? No. It's actually the other way around. So this is the first, major challenge we had. In our team, none of us are domain experts. There are a lot of curves like this that have some really obvious red herrings, a lot of periodicity that actually doesn't indicate planets. And there's also a lot of curves with a lot of subtlety that it's very hard to find the signature of exoplanets in them. And that was the first of many challenges that we've faced, but also another one we faced is that a lot of the data we trained on is from collected by organizations that have very strict methodologies. But the reality is, people using our platform might collect data in their own way, different frequency sampling, sampling periods. So it's been an iterative process. We've come a long way from where we started, but we definitely have a lot further to go. Nonetheless, our model's pretty good. We have recall of 93%, precision of 76%. So if you don't do data science, basically the important thing on this table is this bottom row represents stars that do have planets, and this top is ones that don't. This right-hand column represents the fact that our model predicted that that star has planets, and the left one is our model predicts that it doesn't have planets. Recall is just focusing on this bottom row. And high recall basically means that we have quite accurately avoided incorrectly predicting that a star that does have planets doesn't have planets. So in practice, that means that if we had 14 stars that do have planets, only one of them would slip through our algorithm undetected, which we're pretty proud of, I'm not going to lie. On the flip side, we have precision, and that is basically our model's ability to avoid incorrectly predicting that a star does have planets when it actually doesn't. And what that means practically, in essence, is if we had to send out a load of probes to all the stars we thought do have planets, about 1 in 4 would show up duds, but 3 in 4 would actually find there are exoplanets when they arrived, which, if we were looking to allocate resources for a future mission, that's really important. A high-precision model is very important, because we want to avoid wasting resources, sending probes out to distant stars where there's really nothing to be found. But that's not what we were trying to do. We have made a high-recall model which quite accurately culls all the planetless stars that we don't want without actually culling too many false negative stars. That's stars that do have planets, but that our model thinks doesn't. But there's still a lot further to go. There's a lot more we want to do. We have a viable platform, but we do want to make it a little bit more usable for a wider range of users and user inputs. So as I mentioned earlier, we would like to generalize the model. Different people might take different sampling methodologies that our model currently wouldn't necessarily be able to account for. We want to expand that. We also want to extract greater planet information. So maybe we want to be able to say how many planets, their atmospheric composition, their orbital periods, things like that. But we're also looking for a lot more suggestions, inputs from anyone, especially those, if anyone has any domain knowledge. We're pretty keen to find things we could do that would improve our product in future versions. But yeah, mostly we just want to say thank you to the TAs, to everyone here who's made it a pretty nice time to be here. Larry, Alexi, my team. It's been a short 9 weeks, but it's been a long 9 weeks. So thank you very much, guys.
We started with the macro. We were looking at the sky. Now we're going to look at the micro. And for that, I'm going to invite Elizabeth on stage for IDC. Let's welcome Elizabeth.
All right. Thank you for that very smooth transition from space to microscopes. Well, as Sivan said, I'm Elizabeth, and my team, Jack and Nadia, who's in Melbourne right now. We're proud to be presenting our project on detecting invasive ductal carcinoma in breast cancer histology images. So the objective of our project was to identify invasive ductal carcinoma, or IDC, in breast cancer histology images, such as those shown on the right, using a convolutional neural network, or CNN model. In 2020, 92,000 women in Japan were diagnosed with breast cancer. IDC is the most common subtype of breast cancer, and therefore we believe that by focusing on detecting and identifying the subtype, we can really accelerate annotations and improve clinical outcomes for the majority of breast cancer patients. So we also believe that deep learning has a unique role in improving the digital pathology process. First and foremost, it can reduce the time between biopsy and diagnosis. Typically, it takes 1 to 2 weeks between actually receiving tissue from a patient and then delivering the diagnosis to that patient. Using our tool, you can provide a rapid second opinion in addition to that of an experienced pathologist, and potentially our tool can even discover cancerous regions that were missed by the pathologist. For example, on the screen you can see a pathologist annotation shown in green, and then below you can see a deep learning model's annotation where it actually captured some true cases of IDC that the pathologist missed. Without further ado, though, let's show you our app. So let's say you're a pathologist and you have an image that you've just received from a lab technician and you're ready to annotate it to determine the diagnosis for the patient. All you need to do is upload the image and wait 1 or 2 minutes and you'll have the annotation. So we're using deep learning, and deep learning is a subset of machine learning that uses neural networks. In particular, we're using something called convolutional neural networks. And convolutional neural networks are a tool that allows a machine to identify important features for a particular task. Our task was, of course, identifying IDC, and that was the role of our convolutional neural network, to pick out those important features or traits in the image. We use 3 metrics to evaluate our model: precision, recall, and F1 score. So simply put, precision is how well our model does at distinguishing between IDC and non-IDC images. Recall is how well our model captures all true cases of IDC in a breast cancer histology image. And finally, weighted average, or F1 score, is like weighted average, but it's a little bit different, and it takes into account recall and precision. So after the user uploads an image, we add a bit of padding to make sure that the margins of the images are multiples of 50. Then what we do is we slice it into 50 by 50 pixel images. Each of these slices is then sent to our model. Our model makes predictions and then re-stitches that image back together with the predictions attached. For those of you familiar with deep learning, our model is relatively simple. We have 2 convolutional layers, each followed by a max pooling layer. Then we have a flattening layer, a dense layer with 16 neurons, a dropout layer, and then finally, our binary output: yes, IDC, no, IDC. So after our program makes the predictions, we create a heat map using something called GradCam, which is Gradient Classification Activation Mapping. Simply what it does is this heat map is based on the importance of each pixel in the final decision. The more important, the more red it is. The less important, the more blue it is, right? We create a threshold that cuts off anything that is not deemed as IDC. So anything that you're actually seeing on the heat map, that like light blue color, indicates some level of IDC. With that in mind, let's see how well our model did. There we go. Cool. So our original image is on the left, and on the right side, you can see the heat map that our model generated. If we zoom in just a little bit, we can see some of these regions of interest in more detail. So as I said before, the regions that are like a light blue to a green color, these are low IDC severity. As we get to the yellow, red, orange, these are medium severity. And then ultimately, there are some regions that you can see in there that are high severity IDC. At the bottom of the report, we also provide a succinct summary of what our model does. It found that about 57% of the image is IDC free. However, almost 7% contains regions of high severity IDC. Therefore, our model makes a recommendation that says, further testing strongly recommended. Depending on what the model finds, it will make a different recommendation. If there's no IDC, it will say routine testing recommended, right? Or consider further testing. But how well does our model actually do? So our model outperforms that of previously published papers using the same data set. We happen to get an F1 score of 79%. However, our balanced accuracy suffers a little bit relative to those 2 publications. The reason being is that we really prioritize recall. We wanted to capture as many possible instances of IDC in these breast cancer histology images. With that said, there were some challenges along the way. We started off with a relatively small number of labeled training data, and therefore we had to use data augmentation to sufficiently train our model. Additionally, none of us are medical professionals, and so we have to rely on the somewhat agnostic decision of our CNN model as to whether or not something is truly IDC or not IDC. Next steps for improving our model would be to first extend the model training time. We only trained our model for about 2 hours, and we could definitely go further. The literature suggests that training it for an additional 20 hours on the same data set will improve the scores substantially. Additionally, we'd like to explore some transfer learning, right, where we take a previously successful model made by some other researcher and employ it on our data set or on our problem. Finally, if we were to put this in a clinical setting, we definitely want to improve the user interface. For example, adding a print report or an email report function, making it as easy to use, as easy to interpret as possible for a pathologist and the patient. So with that in mind, we hope that our tool can help to accelerate annotations, improve patient care, and potentially save lives. With that, I'd like to thank the team, Jack Clare, Nadia Yap, and of course, La Wagon for the opportunity to study data science these past 9 weeks. Thank you.